time and clock synchronization in cloud data centers. Preface. Content of this lecture: we will discuss the fundamentals of clock synchronization in cloud and also its different algorithms. Before that, we will discuss the importance of time in the distributed system and the cloud systems. We will also cover causality, a general framework to avoid the physical clock synchronizations using logical clocks, and we will cover the different logical clocks such as Lampert clock, vector clocks, to capture the causality between the events in the distributed system and the cloud system. So, let us see the importance of time. So, time is one of the most crucial in the distributed system and as also in the cloud system. But the support for the time and the clock synchronization is non-trivial, it is difficult. In this particular discussion, we will first understand why the timing is required to be maintained in the distributed systems and in particular the cloud computing systems. Let us see that you want to catch a bus at 9:05 AM, but your watch is off by 15 minutes. In case your watch is running late by 15 minutes and the bus will depart at 9 o'clock. So, definitely you are going to miss a bus. On the other hand, if your watch is running fast by 15 minutes, then you will reach earlier and unfairly waiting for a longer time. So, this brings up the synchronization of the clock, and we have also seen that if the clock is running late, then you are going to miss a bus. That means to run the applications and that to ensure the correctness, the clocks need to be synchronized. Hence, the correctness is required using the time synchronization of the clocks in the distributed systems. Similarly, if your watch is fast by 15 minutes, then you will reach earlier and you will be unfairly waiting for a longer time. This leads to a fairness, that is the compromise with the fairness. So, the time synchronization here also requires that to ensure the fairness in distributed system and a cloud computing system. So, therefore, to ensure the correctness and fairness in the distributed systems and the cloud systems, to ensure correctness and fairness, there is a need to synchronize the clocks running in these systems. Now, the question is, we will see how this particular synchronization is to be done in such a system. Now, synchronization of a clock in a single system is quite trivial, but if there is a distributed system and a cloud computing system where the time is distributed, then the synchronization of the clocks to have a consistent distributed timing at all different locations is non-trivial, it is very difficult. So, we are going to see the second case here in our model, which is nothing but a distributed system and the cloud computing system. To ensure a distributed clock synchronization. So, as we have already seen that time synchronization in this environment, that is in the distributed model, ensures the correctness and fairness in the different services and applications. For example, let us say that we are running a airline reservation system using cloud, and we will see the scenario where the synchronization of the clocks are required. So, assume that there is a server X on the cloud and there is another server Y and a client request for a reservation. So, the client will send a request to purchase a ticket, which is the last ticket on a particular flight, which is maintained at the server X. Server X timestamp the purchase as 6 hours and 25 minutes. That was the last ticket. Then after the purchase of the ticket and that timestamp at which time this particular ticket was sold out to the client, it will be logged and it will send the reply OK back. Since that was the last seat, server X responds to the client, and when the next request now comes from through the server Y about booking another ticket for the same flight, which is already full. So, the server X will send the message that it is full to the server Y. Now, Y will enter that the flight is full and will store this information with its own local time. So, his clock will give another time, that is 6 hours 20 minutes. Now, another server Z queries to X and to Y regarding this particular flight seats, but when it gets this information that server X has booked the ticket, the last ticket at 6 hours 25 minutes and Y at the time 6 hours 20 minutes, the flight was full, then in that case the server Z will be confused. Why? Because the earlier time, that is 6:20, the server Y is showing that all the seats are full, whereas later time, that is 6:25, the server X could book a ticket, that is the last ticket. Why this problem is there? Because both these server X and Y, their clocks are running different timings, hence their clocks are not synchronized. So, this particular problem arises because the clocks at X and Y are not synchronized. Now, what are the key challenges in clock synchronization problem in a distributed systems and the systems like cloud? Now, here the hosts which are the part of a cloud system and which are internet based connection with each other, each host in this scenario has its own local clock, and unlike the CPUs within one server or a workstation which share a common clock, here there is a internet based connectivity. So, they have the network and through the network they can communicate, they do not have any shared global clock. So, that becomes a problem. So, the processes in the internet based system follow an asynchronous distributed system model. Asynchronous model we have seen in the earlier lecture that their messages when they communicate, for example, these two clocks are running in two different cloud systems, they can only communicate through the messages, and these messages, the delays are not predictable or these delays are not bounded. Similarly, the processing delays are also not bounded in such a system. This asynchronous model is different than the synchronous model where in such a system there is a common shared memory where the messages delays are bounded. So, in this scenario the clock synchronization, that is in the cloud system, the clock synchronization across different hosts is non-trivial, and we will see that in the asynchronous model how the clock synchronization will create a problem, and then we will see the technologies or techniques to solve it. So, let us see the definitions of this asynchronous distributed system model. So, let us consider that the distributed system, which is an asynchronous model, consists of number of processes, and each process has its defined state. So, state of a process comprises of its data, its stack, its heap, its program counter, and different registers. So, it is all collapsed and we call it as the state of a process. Now, this process takes different actions to change its states, which may be an instruction or a communication messages. So, that means there are three different ways the states can change. The first is when the instruction is executed, the second one when a communication takes place, that is in the form of a send or a receive of a message. So, in turn we define there are three different events in the state transitions of such a model. They are the internal events in the form of instructions, then send of a message is an event and a receive of a message is an event. So, each process has a large clock and the events within a particular process, which is called a internal events, can be assigned with a timestamp of its local clock, and all the events which is called internal events ordered linearly. But in a distributed systems, where there are a large collection of such hosts which runs their own clock. So, we need to know the order, we need to know the time to order the events across the different processes. Let us see the example using this particular diagram, that a particular process 1, its events 1, 2, 3, 4, 5, they are being timed through a local clock. Similarly, this event P2 also has its own clock and can order the events 1, 2, 3, 4 and 5, 6. Similarly, P3 also has the local clock which can time these events, and using that time all these events can be linearly ordered, that is shown here in this space time diagram. However, if we take all the events and want to order them, then there is no global clock which can order all the events. There is no global clock. Which can order all the events in the distributed system. So, to do this, to see how this, in the absence of a global clock, how the events are to be ordered in a distributed system, we will see through a systematic theory. So, let us see some more definitions in this respect. First, we will see the two definitions. One is called clock skew, the other is called clock drift. Now, as you know that each process is running its own local clock. So, when you compare the clocks of two different processes, so there are two things which will immediately be. One is the current timing of both the clocks. Now, if these times are not same, they are different, then it is called a clock skew. So, clock skew is nothing but the difference in the timings across two different clocks running in different processes. Just like on the road, two vehicles are running. So, the distance between these two vehicles is called the skew. Similarly, the clocks are running with the different timings. So, the difference in the timings is called a clock skew. Now, second definition is about the clock drift. Now, these clocks runs with a different speed. Speed of a clock 1, speed of a clock 2. Sometimes it is also called as a rate, and some people also call it a frequency by which these clocks are running. If they have the same speed or a rate or the frequency, then there is no clock drift. But if the frequencies or the speed is different, then it is called a clock drift. So, that relative difference in the clock frequencies of the rate or the rates of the two processes is called a clock drift. For example, two vehicles which are running on the road with a different speed. Let us say it is 80 km per hour and the other one is quite slow, that is 40 km per hour. So, their speeds are different. So, although the 80 km per hour, that is a fast running vehicle, is behind the slow running vehicle, but after some time it will cross and then will run away, then that means drift apart, drift away. So, the speed is also important. So, the timing, the difference in the timing is called as Q, and the difference in the speed is called the drift. So, in this particular clocks or multiple clocks where more than 2 clocks are there, then these two factors are going to play an important role in the synchronization. So, therefore, a non-zero clock is Q implies that the clocks are not synchronized, that means they are giving different timings. Just like in the previous example, we have seen one clock was giving the time 6:25, the other clock was giving the time at 6:20. So, they are running at different timings. So, non-zero clock is Q implies that the clocks are not synchronized. A non-zero clock drift causes this is Q, that means the difference in their timing to increase eventually. For example, if a faster vehicle is ahead, then it will drift away, and if the faster vehicle is behind, then it will catch up and then it will drift away. So, having understood the clock skew and clock drift, let us see the clock inaccuracies. So, as far as the physical clocks are concerned that we use, so not only they have to synchronize with each other, but also has to adhere that physical time, that is the physical time, a common time or accurate time, that is called physical clocks. So, how to get that particular correct time, so that you can synchronize your physical clocks. So, physical clocks are synchronized to the accurate real time with a standard like UTC, universal coordinated time, which is supposed to maintain the correct time at all point of times. However, due to the clock inaccuracies, a timer or the clock is said to be working within the specifications. So, let us see what are the specifications. Now, if a constant rho is the maximum skew rate specified by the manufacturer, it has to be bounded within 1 plus rho and 1 minus rho. So, let us see that dc by dt, if it is 1, then it is the perfect clock, that means it is synchronized with the standard time. Now, if dc by dt is less than 1, then it is a slow clock, and if it is fast, then it is a fast clock, and if it is bounded by these values rho, that means this is 1 plus rho and this is 1 minus rho, then this is acceptable as far as manufacturer is concerned, but beyond that it need to be designated as clock inaccuracies. Now, the question is how often you need to synchronize the physical clocks. That depends upon a parameter which is called a maximum drift rate MDR of a clock. The absolute MDR is defined to be the relative to the coordinated universal time UTC. So, MDR of any process depends on the environment. So, the maximum drift rate between the two clocks with the similar MDR is equal to 2 times MDR, because if we consider two clocks, maybe one clock is running behind with the rate MDR and the other clock is running ahead of MDR, then total drift rate here in this case will be 2 times MDR, that is the maximum drift rate. Now, given the maximum acceptable clock skew, that is m, as you know that this is the time between any pair of the clocks. So, therefore, the time duration when they are required to be synchronized will be this m divided by this drift, that is 2 times MDR. So, this is the interval when the clock needs to synchronize. After every such interval, the clocks needs to be synchronized. So, having seen this kind of equation, now we will consider two different type of synchronizations. Now, if we consider a group of processes in our model of a distributed system and the cloud system, there are two kinds of synchronization possible. One is called external synchronization, that means if the processes used to synchronize their clocks with a external clock, that means not in a group, that is external clock which maintains the correct time, then it is called external synchronization. For example, if a process Ci's clock is within a bound D of a well known clock S, external clock S, then Ci minus S, that means in the absolute form, that clock drift is to be bounded by D at all points of time. That means it has to be synchronized, that is Ci's clock has to be synchronized whenever there is a violation of this condition. This external clock S is nothing but it is always synchronized at any point of time using universal timing, which is also called as a universal coordinated time UTC, or the timing which is basically maintained as per the atomic clock. There are two algorithms for this external synchronization we will cover in this discussion. The first one is called Christian's algorithm, the second one is called network time protocol, NTP. On the other hand, the group of processes will synchronize their clocks within a bound D without the external clock. So, that means between any two process I and J, if their clock values is having the difference or a skew, then it has to be bounded by D at all points of time. This synchronization can be achieved using the algorithm which is called the Berkeley's algorithm, and we will also see the algorithm which is called a data center time protocol, DTP. Now, one small note to see here is that external synchronization with the bound D will basically implies that it is the internal synchronization with a 2 times D, whereas if it is external synchronization, that does not implies anything with the external synchronization, because of the fact that entire system may drift away from the external clocks. Basic fundamentals of external time synchronization. So, let us see through this example. So, all the processes, let us say that P will synchronize using a standard time server S, which maintains the accurate time. So, such process P sends a message to S, what is the time. So, S will check the local time to find out the time, let us say T, put in a message and send the message back to the process P, here is the time T. So, when the message received by P, it will set its clock as time T. So, in this particular manner, what is the problem? What is the wrong? So, the problem is that by the time the message is received at P, the time has moved on. Take this particular example. So, this is the time, let us say at this instant of S, the time is T, but when the message is sent to T, this particular time, when this is set as time T, the time of the server S will be now T1, that means it is a different time. But here the time which is set by P will be the old time. Hence, by the time the message is received at P, the time has moved on. So, P's time, if it is set to T, will become inaccurate. Now, the inaccuracy is a function of message latency. So, inaccuracy is this particular function of a message latency. That means, if we know this latency and is informed to P, so P can set this particular value, so that it can also be accurate, or it can reduce the level of inaccuracy. Since the latencies are unbounded in a asynchronous system, the inaccuracies also cannot be bounded. Hence, this particular simple method of synchronizing the clock through a time server S using an asynchronous system through using message passing will have an inaccurate time set. Let us see how different algorithms resolves this particular inaccuracies. Christian's algorithm. P measures the round trip time, which is called a RTT, for the message exchange. So, suppose we know the minimum latency from sending the message from P to S. Let us say this is minimum latency, and the minimum latency, if it is traveling from S to P, is called as min 2. So, min 1 and min 2, these latencies highly depends upon the operating system overheads to buffer the messages, than TCP time involved to queue the messages, etc. So, the actual time at P when it is received, the response is between T plus min 2 and T plus RTT minus min 1. So, let us see what is the minimum response. So, minimum response is, so the actual time at P when it receives the response, the minimum of that bound is T plus, because here this is the time T which is stored and sent. So, this particular latency will be added. This is the minimum of latency which is involved. And what is the maximum of these values? So, maximum of these values will be the time T plus, this is the round trip time RTT, that is this particular entire time is RTT. So out of RTT, let us say this particular time, which is called min 2, if we subtract out of min 1, RTT minus min 1 will be this much of the maximum time. So T plus RTT minus min 1 will be this particular time, and this will be added here. So that will be T plus RTT minus min 1. So this is the bound, that means the inaccuracies. So the actual time at P when it receives the response falls the minimum of this particular time T plus min 2, and the maximum that is upper bounded by this particular time T plus RTT minus min 1. So P will set its time to the halfway through this particular interval. That means T plus RTT. So what is that interval? If we recall, that interval will be T plus RTT minus min 1 minus T minus min 2, that is RTT minus min 1 minus min 2. So this is the interval, and halfway of this will be divided by 2. So let us see. So halfway will be that RTT plus min 2. So the error will be at most RTT minus min 1 minus min 2 divided by 2, that is this halfway. So this will be the error, and it is bounded by this corresponding value. So again let us see through this particular illustration that this is the server which maintains the time, and this is the client which want to synchronize its clocks, assuming that minimum 1 minimum 2 is equal to minimum, both are equal in that case without loss of generality. For the sake of simplicity, let us understand this. So the earliest time when the client message will be received is that start from T0 plus T min. Similarly, the server will respond and the reply will be received. The latest time will be when the server sends plus T min. So that particular range will be that T1 minus T0 is the round trip time, and 2 times that minimum value, because both are same. It is same as the equation which we have seen. And if we divide by 2, this becomes as this is RTT minus this is T min. So this is the accuracy of the result of Christian's algorithm. So here, as far as error bounds are concerned, we know that in the synchronization of the clocks, we always increase the clock value but never decrease it. So if you ever found to be the requirement to decrease the value, that you don't do it, leave it as it is. So it is allowed to increase or decrease the speed of the clock then. So if the error is too high, it will take multiple readings and average them. Let us understand through another example. Here the server sends, this is, let us say, the client will send at T0 the request, T0 is 58, it will receive the response at 58:15:900. The response contains the timing of the T server. So, it is T0 and T1 and T server time is 50925:300. Total elapsed time is in that particular message, that is the difference of timing T1 minus T0, that comes out to be 800 milliseconds. So, if you guess as per the Christian's time, so that means RTT divided by 2, that means the guess says that around 400 milliseconds the message was being originated by the T server. So, the time which will be set by the client will be the time which is sent by the T server plus this particular average elapsed time, that is 400. So, the server time is 50925:300, the T server plus this offset value is added, comes out to be this much time. So, the clock will be set, the client will set the clock value as this one. Here we can see that T min value is 200 milliseconds. Why? Because it is a 400. So, it is 200 and 200 becomes 400 here in this particular case. Now, we will see another time synchronization protocol which is called a network time protocol, NTP, which is in 1991 and 92 it becomes an internet standard, RFC 1305. Here it is assumed that the network time servers, they are organized in a form of a tree and each client will be at the leaf of a tree. This particular tree hierarchy of the servers are such that every child will synchronize with its parent server. So, on the top, let us see, you have a primary server which is assumed to be synchronized its time, and secondary server will synchronize their time with the primary server, and tertiary server will synchronize their time with the secondary server, and client will synchronize their time from tertiary server, and so on. Let us see the details of network time protocol. Here let us see that, so every child will now synchronize its time with the parent. So, child will send a message, let us start the protocol, and at time Ts1 the parent will send a message 1, and this particular message 1 will be received by the child at time Tr1. Then child will send another message, message 2 at the time Ts2, and this particular message will be received by the parent or the server as at Tr2. Then this particular parent will pack these two messages Ts1 and Tr2 here and send in a message which will be received by the child. So, child will now have its own timing Tr1, Ts2 and these two messages which is received from the message, that is Tr2. So, Tr1, Tr2, Ts1, Ts2, all 4 values it has now received. Let us see how this network time protocol uses all 4 values to synchronize the clocks. So, using these 4 values, it will calculate the offset O using this formula TR1 minus TR2 plus TS2 minus TS1 divided by 2. Let us see how this offset value is calculated. So, for that let us calculate the total error. Let us assume the real offset is O real, and we also assume that the child is ahead of the parent by this value O real, and the parent is behind the child by O real, which is written as minus O real. That means parent is ahead of child by minus O real. Suppose one way latency of a message 1 is L1 and the message 2 is L2. Then let us calculate the TR1. So, here let us calculate TR1. TR1 is equal to TS1 plus, let us say this particular latency is L1 plus the child is ahead of the parent by O real. Similarly, we can calculate TR2. TR2 is equal to TS2 plus this latency is L2 minus O real, that means the parent is ahead of a child by minus O real. So, this is equation number 1, this is equation number 2. Now, we subtract 2 from 1, we will get TR2 minus TR1 is equal to TS2 minus TS1 plus L2 minus L1 2 times minus O real. So, it comes out to be O real is equal to, this will go on the other side, and TS2 minus TS1 then minus TR2 plus TR1. This is one factor plus L2 minus L1, and this will be divided by 2. So, this particular value, if we rearrange, it comes out to be TR1 minus TR2 then plus TS2 minus TS1 divided by 2, that we have already obtained this value, plus L2 minus L1 divided by 2. Now, this is an offset. So, O real is equal to offset plus L2 minus L1 divided by 2. So, here we have obtained up to this stage O real is equal to offset O plus L2 minus L1 divided by 2. So, if offset we will take on the left side. So, O real minus offset, absolute value will be less than L2 minus L1 divided by 2, and this value is also bounded by L2 plus L1 divided by 2. So, this is the error bound. So, this particular error is bounded by the round trip time, that is RTT. Now, we will see another algorithm, that is called Berkeley's algorithm, and this is the algorithm for internal synchronization, whereas the previous algorithm which we have seen was an external synchronization. Here, out of the group of processes, one of these processes will be elected as the master using any leader election algorithm, and this master will poll each other machines periodically, that is, it will ask each machine for its time. Now, as far as the message latencies are concerned, which basically will be obtained through the previous algorithm, that is the Christian's algorithm. Now, when these results are computed, then using the master's time, it will be computed as the offsets. Why? Because the average cancels out the individual clock's tendency to run fast or slow. So, only the offset will be calculated by which each clock needs to be adjusted to each slave. Let us take this particular example to understand this. Let us see 1, 2, 3, 4. In the system there are 4 processes. Out of them, one is the master plus 3 slaves. So, the master will ask their timings, master will ask the timings of the slaves. So, slaves will send the timing to the master in this particular way. So, for example, slave 1 is having time 3:25, slave 2 is having time 2:50, slave 3 is having time 9:10. When all these values will reach to the server, server is having time 3 o'clock. So, server can find out the skew of these particular timings. Now, 3:25 and 2:50 according to server's time is good enough, that means around his timing they are running their clocks, maybe with some skew. As far as 9:10 is outlier, so it will not consider in averaging this particular time like here. Now, then it will calculate the average, that means it will perform the averaging using his value, and this average comes out to be 305. So, with this 305, this particular time requires this particular offset for server for the slave number 1, this offset for the slave number 2, that is plus 15, and this offset will be calculated for the slave number 3, and this will send to the each client, and hence the Berkeley algorithm will synchronize, will do the internal synchronization. Now, we will see another time protocol which is also the internal synchronization, that is called data center time protocol. So, this particular protocol is published in a paper that is called Globally Synchronized Time via Data Center Network, which is published in ACM SIGCOMM 2016. Here it considers the layers of the network also into an account for calculating different parameters. So, DTP uses the physical layer of the network So, for example, humans use causality at all points of time. Take the example that I enter the house only if I unlock it. So, that means unlocking of an event, the time of that should always be less than the time when you enter the house. So, that means unlocking happens before the entering into the house. The second example is that you receive a letter only after I send it. So, the sending of a letter happens before the receive of a letter. So, that means this particular way humans are basically using the physical clock, and now they are basically ordering the event. For example, here unlocking first and then entering the house, or sending letter first and then receiving it later. So, without using physical clock, if we can obey this causality, then that concept can be used without even the synchronization of physical clock. This concept was called as logical ordering, given by or it is also called as a Lamport ordering, which was proposed by Leslie Lamport in 1970. Almost all distributed system and the cloud system since then are applying this concept. So, these are the details of the Lamport's contribution, and for which he has got the Turing Award, that is time, clocks and the ordering of events in a distributed systems. So, let us see the logical ordering or a Lamport ordering, which defines the logical relation, which is called happen before relation between the pair of events and is denoted by an arrow. So, this happens before relation is denoted by an arrow. This happens before relation follows three different rules. The first rule says that on the same process A has happened before B if the time of A is less than time B, using the logical clock. The second rule says that if P sends a message M to P, then send of message M has happened before the receive of a message M. Third rule is the transitivity, which says that if A has happened before B and B happened before C, then A has happened before C. These three rules will create a partial order among all the events in the distributed system. Not all events are related to each other, that is why it is a partial order via happen before relation. Let us see through an running example. Here we have P1, P2, P3. P1 is having the events A, B, C, D, E, where A is internal event, B is a send of a message, F is a receive of a message at the process P2. Similarly, event J is the received of a message from P1 at P3. Let us see that A has happened before B. So, A has happened before B, this we can get through the timing of the internal clock. Why? Because A and B they are internal event, hence the time of A is less than time of B. So, it follows A has happened before B relation. The second one is B has happened before F. So, B is a send of a event. So, the time of the sending of an event, which is maintained by P1, is less than the time when the message is received as far as the rule 2 is concerned. Hence, B's also happened before F. Similarly, A's happened before F. So, by transitivity property, that means A's happened before B and B's happened before F. Therefore, A's happened before F through the transitive property. So, there is a causal path. This is also called a causal path. So, if there exists a causal path, it will connect all the events using this happened before relation. Similarly, let us say that H has happened before G. Here this is the H has happened before G. So, there must exist a causal path which connects H to G. That means, H is a send off event and E is a receipt of a message. So, H has happened before E. Similarly, E and F, they are the internal events of P2. So, E has happened before F and F and G, they are internal events of process P2. F has happened before G. So, using transitivity property, H has happened before G. Similarly, F has happened before J. So, F has happened before J. So, there must exist a causal path. Similarly, H has happened before J. So, H has happened before J, there exists a causal path. C has happened before J. So, from C there exists a causal path which connects C and J, and hence this particular Lamport clock is able to capture the causal relation. Now, the implementation of these time stamps to each event, so that let us assign a logical time stamp without a physical clock which will obey the causality. Let us see the implementation using a logical clock which follows the two different rules. The first rule says that each process uses a local counter which is called a logical clock, which is nothing but an integer which is initialized to 0. A process increments its counter when it executes a send of a message or the internal execution of an event happens within that particular process. The counter is assigned to the event as its time stamp. So, the process increments its counter whether it is an internal event or it is a send of a message event, and this particular time stamp will be carried with the send of a message. So, this is the rule number 1. The rule number 2 says that when a message is received, a receive of a message event will update the counter in this form. First of all, the time stamp which is carried in the message and its local clock, the maximum of these two values will be taken up and it will be incremented. That is rule number 2. So, this will provide the Lamport's time stamp. Let us see through an example. Here all the counters are initialized to 0 as we have seen in the implementation. Then process P1 will have its local clock, it will be initialized to 1 or will be incremented from 0 to 1 because it is an internal event. Similarly, as far as process 3 is concerned, the send of a message, hence its clock will be incremented from 0 to 1 and this will be contained in the message and will be sent. Similarly, when the message will be received, then we will follow the rule R2 which says that the message which is carrying 1 and the local clock is 0, the maximum of 0 and 1 will become 1. and when it will be incremented, the time stamp here will be equal to 2. Now, when this particular message will be received, here we can take the maximum of 2 and 2, that become 2, and plus 1, that become 3. This particular event 3 plus 1, it will become 4, and 4 when it will reach over here 4 and this is 3, the maximum is 4 plus 1, that becomes 5, and 5 plus 1, this will become 6, and when it will reach over here, so the maximum of 6 and 1 2 2, that becomes 6 plus 1, that is 7. So, all these we have already explained, and they are obeying the causal properties. For example, A has happened before B, so the time stamp also is less in case of A. B has happened before F, so the time of B is less than F. A has happened before F, so the time stamp A is less than F. Now, we have seen the example of the events which are causally related, they are following the Lampert's logical clock, but not all events are causally related. That means not always implies the causality among all the events, that is why it follows the partial order relation. Let us see through the example C and F. Although their time stamp is 3, so do we infer that C has happened before F? Similarly, H and C, H and C. So, the time of H is 1 and the time of C is 3. So, can we infer that H has happened before C? No, we cannot. Why? Because they are not causally related. Hence, they do not follow this happened before relation. Hence, they are called as concurrent events. So, CF and HC, they are the pairs which are not obeying the causality relation, hence they are called concurrent events here in this case. So, a pair of concurrent event does not have the causal path from one event to another. So, Lampert time stamp not guaranteed to be ordered or unequal for concurrent events. This is okay since the concurrent events are not causally related, but what we can see here as a takeaway that if E1 has happened before E2, this implies that the time stamp of E1 is less than the time stamp of E2. This is what is known here in our logical clock given by the Lampert. But if we see the time stamp only and can be infer whether the events are happened before or they are concurrent, that we cannot, just by looking the time stamp we cannot infer whether the events are happened before, or that means causally related, or they are not causally related, they are concurrent event. That is the drawback of the Lampert's clock. So, the next clock is called a vector time stamps or vector clocks, which is used in the key value store like REAC. Each process uses the vector of integer clocks. Suppose there are n processes in a group 1 to n and each vector has an elements. So, process I will maintain the vector I for each process 1 to n. Now, jth element of the vector at process I is denoted by this, is the which indicates that the process Pi's knowledge about the events at process J. So, this particular notation we are going to use further in this understanding of vector clocks. Assigning the vector timestamps, that is, on an instruction execution or send of an event at process I, it increments only its ith element of its vector clock, and this particular timestamp, the entire vector will be timestamp, and so the message carries the send events vector timestamp within it. When the message will be received at a process I, then process I will increment its vector, as we have seen. This is as per the Lampert's clock. And then it will take the maximum of the vectors of j and its knowledge about other j excluding its own vector. That means, the message, the vector of the process j will be used to update its own clock. So, this is a new step, that is about update the knowledge of process j at I. So, whenever there is a message exchange, the clock values will be updated based on the information which is being sent, the knowledge of other processes. So, let us see through an example. Here all the counters are initialized to 0. Now, with the event at P1, only his clock value will be incremented. Similarly, for P3, only this value will be incremented, and whenever there is a message exchange, then these other values will also be updated. For example, the receive of a message will increment its local variable, but the message contains the information about the P3's knowledge. So, this will be updated. So, here it will be updated for the other values. So, vector timestamp will not only update its knowledge, but whenever a message exchange, it will update its vector based on the information of the other processes. So, this is another example, that if when P2 will send this message with the timestamp 200, and it will be packed as a message when it will receive at P2, then P2 will increment its local clock as per the Lampert's logical clock, whereas 0 and 2 they will update to the maximum of 2. So, 1 and 0 will be updated over here. So, this is not updated, same value will be, because it has more knowledge than the P1 about P3. Now, we will see that using vector clock we can perform some operations on the vectors, and this will be used to compare the vectors. Just by looking the vector, we can infer whether two events are causally related or not. So, that means if the vector Vt1 is less than vector Vt2, this will implies that there exist two vectors which are Vt1 is less than or equal to Vt2, and also there exists a particular value which is strictly less than, then basically this particular condition holds, and that shows that two events are causally related. So, two events are concurrent if neither Vt1 is less than or equal to Vt2 and nor Vt2 is less than or equal to, hence they are causally related. vector timestamp obeys the causality relation. This also helps in identifying the concurrent events. Let us take an example. So, C and F. So, vector C is 300, F is 211 and 211. Now, this particular value is higher than this one, whereas the other elements, they are less than these values. So, it is not less than, that means there is no, neither C is vector of C, neither it is less than or equal to vector of C F, nor vector of F is less than or equal to vector of C. Hence, they are C and F, they are concurrent events. Similarly, H and C, you can see that this one is less than 3, H and C. So, 0 is less than 3, that is fine, this also is fine, but 1 is greater than 0. Therefore, the same principle, it is neither less than or equal to. So, that means it is not obeying the causality relation, hence they are concurrent events. Summary, we will see that Lamport timestamp uses the integer clocks to assign the events, obeys the causality, but cannot distinguish the concurrent event. Vector timestamps obeys the causality by using more space and also can identify the concurrent event. More space in the sense, here the vector is required to be sent in the message. Is an additional overhead of using the space. So, conclusion, clocks are unsynchronized, or the synchronization of a clocks in a asynchronous distributed system using physical clock synchronization methods, which we have seen, are having the inaccuracies. So, we have seen the methods for doing the clock synchronization in the distributed system. Let us say that they are Christian's algorithm, Berkeley's algorithm, network time protocol, DTP, but all these particular synchronization algorithms, they have the error which is a function of round trip time. So, we have seen also the method by avoiding the time synchronization and also ordering the events using the methods such as Lamport's clock, vector's clock. Thank you.